the rank of some matrix A, which has some number of rows by some number of columns, is equal to the common dimension of the row space of A and the column space of A. So remember that when we reduce the matrix to row echelon form, we had the leading ones in each row, determining the dimension of the row space, in this case being 3, and that was equal to the same as the dimension of the column space, which is obtained using the corresponding columns to these rows with leading ones. And because the dimension of the row space of the reduced matrix to row echelon form is the same as the dimension of the row space of matrix A, and the dimension of the column space of both matrices is also the same, then you can see why this relationship holds. So therefore, given a dimension of the row space of the reduced matrix is 3, then the rank of this matrix is 3. Now the nullity of matrix A is equal to the dimension of the null space of A. So recall that we wrote the solution vector is equal to some parameter, being a real number, multiplied by the basis vector, which we obtained by row reduction. So therefore, in this case, the nullity of our matrix A is equal to the dimension of the null space, which is 1. And we can see that the rank of A plus the nullity of A is equal to the number of columns of the matrix A. So in other words, the rank of the matrix A is equal to the number of leading variables in the general solution for the homogeneous system AX equals 0, and the nullity of A is equal to the number of free variables or parameters in a general solution. So here we have one parameter, being t. If we have a consistent non-homogeneous linear system, AX equals B, and this system has E equations and U unknowns. So for example, by looking at A, we have 3 equations and 4 unknowns. Now if A has some rank, then a general solution of this system contains U minus the rank of A parameters. So remember that when we reduce this system to row echelon form, then for the homogeneous system, the solution space was described by one parameter. So as we can see, the number of unknowns is 4 and the rank is 3, which gives the number of parameters in the general solution of the homogeneous system. But also remember that we can express a non-homogeneous solution as a particular solution plus the general solution to the corresponding homogeneous system, which is this one over here. So therefore the general solution of both systems has this many parameters, being the number of unknowns minus the rank of the coefficient matrix. A system of linear equations being ax equals b is overdetermined if we have more equations than unknowns to solve for. So suppose this matrix has p rows and q columns, then if the number of rows is greater than the number of columns, then this linear system is inconsistent for at least one vector b in P space, which is the vector space of P tuples. So note that in this case, our system of equations can look something like this. So we have our matrix A, which is a 3 by 2, and by matrix multiplication, that must be multiplied by a 2 by 1 vector. So we have a 3 by 2 by 2 by 1. So remember, the number of columns in A must be equal to the number of rows in X for this to be a valid matrix multiplication. And therefore our resulting vector on the right hand side will be a 3 by 1 vector. So we have the components b1, b2 and b3. Now if we augment our matrix A with our vector b, and if we subtract 2 by row 1 from row 3, we get a 0 and minus 2b1. And if we subtract 2 by row 2 from row 3, then we get a 0 and minus 2b2. So therefore for this system to be consistent, b3 minus 2b1 minus 2b2 must be equal to 0. So therefore at least one vector b is not going to satisfy this condition, which is the consistency condition for our overdetermined system. An underdetermined linear system, ax equals b, has fewer equations than unknowns that we want to solve for. So consider this matrix being a p by q matrix. Then if p is less than q, our linear system is underdetermined. So in this case, for each vector b in the vector space of P tuples, our system here is either consistent or has infinitely many solutions. So for example, given the matrix A on the left hand side, which has the following entries. So this is a 2 by 3 matrix. So our vector x must have 3 components. So a 2 by 3 by a 3 by 1 matrix results in a 2 by 1 vector on the right hand side. So now let's augment this matrix with vector B. So here we can see that the matrix is already in reduced row echelon form. So therefore we can't reduce it further. So if we designate x3 as the free parameter, then our second equation is x2 is equal to b2 minus 2x3, which is t, and x1 is b1 minus 2x3. So now we can write our solution in matrix form. So we have our solution vector. So we have x1 is b1, x2 is b2, and x3 is 0. And then we take our parameter, which has components of -2, -2, and 1. So here there's no restriction on our vector components, and the parameter t is any real number. So for each vector b, the linear system has infinitely many solutions. Suppose we have a matrix A which has p rows and q columns. There are 6 vector spaces for this matrix and its transpose. So for matrix A, we have the row space, the column space, and the null space. And similarly for the transpose of A, we have a row space, a column space, and a null space. Now given the row space of A is the same as the column space of its transpose, and similarly the column space of A is the same as the row space of its transpose, we have 4 distinct vector spaces, being the row space of A, the column space of A, and a null space of A, and a null space of its transpose. So these 4 distinct vector spaces are called the fundamental spaces of the matrix A. And therefore the rank of A is equal to the rank of its transpose, and therefore this implies that the rank of the transpose of A plus the nullity of the transpose is equal to P, where P is the number of rows in matrix A. So let's verify this for the transpose. So if we augment this matrix with the 0 vector and subtract 2 by row 1 from row 3 and 2 by row 2 from row 3, we get zeros in the final row. And therefore we can say that x2 is 0 and x1 is 0. So therefore the null space has a dimension of 0, and we can say that the rank of the transpose is 2. So therefore that's equal to P being the number of rows in A. Suppose we have a matrix A with p rows and q columns. And suppose we have a subspace of RQ. So for example, that would be the row space of A and a null space of A, because the row vectors have q components. Then the set of all vectors in the vector space of q tuples that are orthogonal to every vector in S is the orthogonal complement of S, which is denoted S with a perpendicular superscript. So for example, if we have A with the following entries and we augment it with the 0 vector, then subtracting 2 by row 1 from row 2, we get 0 and minus 3. And then multiplying the second row by minus a third, we get a 1. So this matrix is now in row echelon form. So therefore the solution tuple is x1, x2, x3. So in this case x3 is 0, and x1 minus 2x3 is 0, so that means x1 is also 0, and x2 can take on any value to satisfy those two equations. So x2 is a real number in the open interval from minus infinity to infinity. And here we have these two vectors spanning the row space of A. So these have components x equals 1, y equals 0, and z equals 2. So that's the first row vector. And the second row vector has components x equals 0, y equals 0, and z equals 1. So it looks something like this. So the span of these two vectors is the xz plane passing through the origin. So any vector in the plane of these vectors can be represented as a linear combination of these row vectors. So as we can see, the null space of A is the line along the y-axis, which is orthogonal to this plane. So therefore the null space of A is the orthogonal complement of the row space of A. And note that this plane extends to infinity in all directions.